Good morning, everyone. Thank you again for being here for our three-part series. We think it's been very successful and we hope that you've enjoyed it. And as we wrap up this duct construction and fabrication seminar, it's my pleasure to once again introduce our presenter, Jeff Parks, who is from National SMACNA. Jeff is a senior project manager at the SMACNA's Technical Resource Department and brings more than 30 years of sheet metal industry experience, starting as a union sheet metal apprentice. His career has spanned through fabrication, CAD, BIM, estimating, project management, and industry leadership. Today, he provides technical expertise and training to contractors across the country and is a recognized voice on HVAC, duct construction and standards, and best practices. Thank you again, Jeff, for joining us today and
Perfect.
sharing your expertise.
Thank you for the introduction, Carmen. Thank you, Christine, for getting this all set up for everybody. Yeah, so today, like Carmen mentioned, this is our third installment and our last installment of this series. And let's just get right into it. Something I do want to point out first, uh, with all the other seminars, we just, if you have questions, you can throw it in the chat. Kind of got my phone positioned here to hopefully, catch some chats, and Christine's going to help, if I miss them. So please feel free to ask a question anytime. Not going to interrupt me. So let's get started. So for today, our topics are going to be exterior components. We're going to go over some casing and plenum construction details. Large duct over 120. I know that we covered this in the first seminar. I got cut a little short on my time with what I wanted to talk about, duct supports for large ductwork. So that's kind of my main focus of putting this one back in this seminar. And then finally, we're going to get into some type 1 kitchen grease duct. So without further ado, let's get started. So exterior components, this is chapter 6 of the HVAC duct construction standards. Couple of things to note. So the designers should consider the following, when designing for exterior components, whether that be ductwork, equipment, and so forth. So number one, waterproofing details, 2, durability, the service life, wind, snow, hail, exterior loads that are going to be put on that ductwork, corrosion, chemical, electrolytic. That one trips me up all the time. Atmospheric, maintenance, repair, air intake, discharge orientation to prevent hazards, vibration control, any screen enclosures that are used that may affect the HVAC system, infiltration, exfiltration, prevailing winds, and that kind of takes us back up to number 6, orientating your air intakes and discharge. You need to know the prevailing winds to make sure you don't discharge something, and then there's an intake right there that's going to pull it back into the system. And then finally, details and resources available from SMACNA standards, which would be your duct construction standards, duct design manual, and the architectural sheet metal manual. So louvers, this is on page 6.2, figure 6-1. This kind of covers louvers and screens. For anybody out there that may be fabricating their own louvers, I know the company I worked for 27 years, we did a little bit of louver fabrication, especially on smaller projects with smaller louvers. But there are some really, really good details in the duct construction standards that give you your, blade and frame gauges based on the widths of that louver. Louver blank offs shall be single wall 22 gauge, minimum double wall insulated or painted if required. I know there's a lot happening on this screen, so I'm not going to cover every single detail, but it gives you sill details, the mullions, and all that good stuff. Figure 6-2, this is on page 6.4. So this here is where you can calculate the louver free area based on the free area calculation, dependent on the type of louver that you're going to use, the type that we have covered here, type 1, uh, type 2, type 3, depending on the frame and so forth. So there's some useful information here to be able to calculate that louver free area that I don't know a lot of people realize are in the duct construction standards. Some rooftop equipment and ductwork. So roof-mounted ductwork and units and roof-supported duct do require a customized design. It's not the same thing as installing the ductwork within the building envelope. You have wind, rain, snow, ice, different loadings that need to be taken into consideration. Those construction details and recommendations would depend on the contract documents for clarification. Um, so the designer must specify constructions that are appropriate for the specific locality and circumstances. Again, depending on the location for snow load, rain load, not rain load, but rain intensity, ice, that needs to be taken into account when designing for rooftop ductwork, especially. Um, any duct penetrations, joints, seams, mechanical connections should be watertight. Receive exterior duct sealant per S 1.9G, and any specifications that are specific for that project. Horizontal ducts should be pitched or installed to minimize excessive ponding or of water. This especially holds true on very wide, large roof duct that's uninsulated or doesn't have any lagging that has that pitched or sloped roof to prevent that. Roof penetrations by duct should have curbs. And then roof openings obviously require coordination with the architectural, structural, mechanical, and electrical contract drawings. And then equipment and duct heights above the roof level may be influenced by snow load, drift, wind, and obviously aesthetic considerations. If you have very wide duct that's, high above the roof, you're not going to want to see that over the roof line, over the parapet wall. So, location's going to be critical for aesthetics. Look, here we have figure 6-3, rooftop duct insulation. This is just a basic generic detail, a little bit of duct coming off a HVAC unit, and then, turning down into your roof curb at your roof penetration. Couple notes here, waterproof all the seams and joints as per the design specifications. The roof curb would be per figure 6-5, which we will take a look at here shortly. And then kind of zooming in here on our unit connection, this can either be a solid connection, based on, whoops, sorry, I got a picture of myself covering this section AA. Again, it's either a solid connection, if the HVAC unit is internally isolated or the duct's internally isolated, or you have your flexible connector somewhere else in that line. Or, in many cases, you're going to tie into that unit directly with a flexible connection for vibration isolation. Here we have 6-4 for supports for roof. Generally it's going to be on a pier or a roof curb base. Sometimes it can be, tied directly into the roof or the roof structure. It all depends on, how the contract drawings are set up and how the roof is laid out, quite frankly. Um, Within this page 6.7, there's some recommended roof clearances for maintenance for equipment and ductwork. Up to 24-inch would be a 14-inch height, all the way up to 61 and wider. You're looking at about 4 foot off of that roof for clearance purposes. Since we were discussing rooftop duct installation, obviously, if you have quite large ductwork or you're going to size your trapeze bar the same way that you would size it if you were supporting the ductwork within the building. So I'm throwing up table 5-3 here. So this is where you would size your trapeze based on the length of that trapeze and the load that it's going to see based off the duct size, the duct weight, the spacings, and all that. And then here I'm showing table 2-40. This is the allowable load for angles as columns. So this is where you can size your support legs using angle. These are unbraced or unreinforced lengths. So kind of looking at the screen here, if you have a 2 foot long angle, and then based off the size, it tells you what load that angle could handle. And these loads are in KSI. So basically, if we're looking at this top row here, 2-inch by 1.25 by 3/16, 2 foot long angle could handle 1,370 pounds. So the 13.7 times 1,000, it's quite a load. So this chart, this table goes all the way up to 14 feet. A couple things to point out: the A7, A36, that's just your grade of steel, and then ND basically means not designed. And then a lot of people up on exterior rooftops like to use framing channel or strut. Table 5-4 is channel or strut that's used as trapeze. So if you go back to that table 5-3, size your angle for the trapeze, you can then come to this table and then get the alternative channel strut size required. Here we have, figure 6-5. So figure 6-3, sorry, rooftop duct installation points you to 6-5 for the roof curbs. So I just pulled a snippet from the gooseneck 6-5 detail. Kind of gives you, a drawing of the different types of roof curbs, looking to be at least 14-inch minimum from the roof surface. There's some alternate flashing details, A and B. Metal flashing should extend, 4-inch minimum below the top of the roof curb for detail B. So that, and the architectural sheet metal manual has many more types of flashing and curb details than we do in the HVAC duct construction standards. But this is what's covered in the standard. And a couple other rooftop equipment and components. These are on pages 6.8, 6.9, 610. We have some details on fabricating rectangular goosenecks, kind of your minimum dimensions from the roof curb, some radiuses, your duct size opening would be, you would want to add 25% on that end. Figure 6-6, we have some intake and exhaust ventilators, construction details. I'm not going to get into all the nitty-gritty notes, but there's a lot of information here to build these intakes, exhaust ventilators, and rectangular goosenecks. And then 6-7 is a large intake or exhaust ventilator detail, fabrication detail, basically. Couple useful conversions when you're working with ductwork up on the roof. 1-inch water gauge equals 5.2 pounds per square foot. I don't know if you recall, probably not in the first or second seminar when we talked about sizing tie rods. So this is that 5.2 pounds per square foot is something you would use in that equation. But what we can do is for loads that are expressed in pounds per square foot, you can multiply that by 0.192 inches water gauge. So what this example here I'm showing you is, so if you have a snow load of 10 pounds per square foot, you could do 10 times 0.192, and that'll equal 1.92 inches water gauge. So what we're trying to do is, when you're building ductwork, that's going to be on the roof, and it needs to handle snow loads, ice loads, wind loads. This is a way to take those loads and convert them into inches of water gauge. So I'll wrap this all up on the next slide, but this way you can stay within the HVAC duct construction standards and not have to go into, say, the rectangular industrial to do, exterior loading. So if any particulate accumulation, in pounds per cubic foot, you would take 0.016-inch water gauge, multiply that by the depth of the accumulation in inches, and this can be used for any load expressed in pounds per cubic foot, insulation and so forth. But for this example, I'm showing 1-inch thick ice, so that would be 1 times 57.6 times 0.016, and that's a 0.92 inches of water gauge. This will hopefully all make sense on the next slide. And then also there's a wind conversion loads. Now this table is not in the HVAC duct construction standards. This is actually out of the industrial, but this is where you can take this table and equate any wind velocity in miles per hour to a wind pressure on the ductwork. So what you can do is, so for this example, say, our base duct construction standard pressure, we're constructing at the 2-inch water gauge, and you're working on a roof where it's in an area that you have a snow load of 10 pounds per square foot. So that equated to a 1.92-inch water gauge. If you had ice, we did this math already, was 0.92, and then we throw a wind load in there, and that equates to 2.5 inches. That's from up here, and also doing the math. So our critical load for this example would be 7.34 inches of water gauge. So essentially, you can build out of the HVAC duct construction standards with snow loads, ice loads, and wind loads. So for this one, instead of just building a 2-inch water gauge, we would be looking at building, 10-inch water gauge, essentially, because there's no 8-inch water gauge. So this is just a way to stay within the duct construction standards and stay out of the industrial. Now, if you have anything that exceeds 10-inch water gauge, then, we would be looking into the industrial. Hopefully that made sense. If not, yell out. Okay, moving on. Casings and plenums. This is covered in Chapter 9 of the standard. So what we have in here, we have construction standards for built-up standing seam casings up to 2-inch water gauge, standing seam casings, alternate casing construction up to 10-inch water gauge, apparatus casing to 10-inch water gauge, inside seam casing, and then TDC, TDF, and double wall. So here we have figure 9-1, built up standing seam casing, and based on, the casing width and height, there's some recommended minimum gauges for galvanized aluminum, gives you your steel angle sizing, and then your standing seam height. And this is only maximum pressure rating for 2-inch positive and 2-inch negative on this type of construction. Here we have figure 9-2. This is the standing seam casing. I know there's a lot happening on the screen. Not going to point out every detail, but it gives you some basic construction details, with a curb, without a curb. So this one's shown without a curb, with a curb at the base. Gives you some fan and duct openings that to be framed, one panel beyond the opening. And then also, if you're in the actual duct construction standard, it gives you suggested sizing for that framing as well. And then the sheet gauges would be per figure 9-1 that we just looked at. And then for tall casings, you can use a flat lock seam or standing seam in the horizontal, and then you would want to stagger that. So that's, whoops, wrong button. Sorry about that. That's kind of what we're indicating here is the staggered seams as well. And then here's going to be your spacing for your seam to your angle. Figure 9-3, the alternate construction. We're going to get into a little bit more detail on this one. This type of casing actually has some tables to give you, gauges, the what I'm calling the panel height, your A dimension, and it's all based on the span, and then the pressure class that you're looking at. And then this type of construction here is for all sides and the roof of that. So you have your A dimension, which is the panel depth. Your B dimension would be A less a quarter, and then you just lock them. You keep locking them in. And then the panel depth is going to follow, from table 9-1, which we're actually going to look at next. So, oh, sorry, this is figure 9-3, the alternate construction. So this correlates back with this type of alternate casing construction. So what we have is based on the span of your plenum, we have 6 foot, 8 foot, 10 foot, 12, 14, 16, all the way up to 18 foot. Our static pressure, 2, 3, 4, 6, up to 10-inch water gauge. And then what, for an example, say we're going to build a 16-foot tall casing, and our construction class is going to be 4-inch. So what we kind of zooming in here, we sort of have 3 options to build. First option would be 18 gauge with the 4-inch panel depth, and then our panel widths the width of them need to be 14 inches. The second option would be 16 gauge panels and 3-inch high depth panels, and then 12-inch wide. And then a third option would be, 16 gauge, 4-inch depth, and then 18 inches wide. So if we just looked at the top one a little bit closer, so this is back on figure 9-3, we're going to use 18 gauge. Our panel depth is going to be 3 inches. That's our A dimension. Our panel width is going to be 14 inches. That's the width of the panel shown here. And then again, this works for the sides and tops. And then if we have any height span greater than 12 feet, which we would have on this one because we were building it 16 feet, we would need to use 2x2 by quarter angle, to divide the span. And then down here, continuous sheet would be preferred for casings over 8 feet high. You may want to have staggered horizontal seams. So table 9-1, that's the table that gives you all the, gauging, the depth and the panel widths. Some notes from that table. So you would use the table to determine the maximum panel width for the load class, panel span, and the gauge. If there was a dash mark within that table, which I'll go back real fast. So see all these dash marks here. That indicates that the panel gauge is not suitable for the load class or the span condition. And then for casings with interior support angle, if you're spanning, that 12-foot, you would use the larger of the spans on either side of the angle to select the panel gauge and width. And then, of course, figure 9-3, that's kind of your assembly figure, giving you all the nitty-gritty details to actually fabricate and assemble it. Some additional comments. So the alternate casings cover up to 18-foot spans at 4-inch water gauge. The alternate casing covers 10-inch water gauge up to 12-foot spans. Other figures within the chapter covers standing seams over 2-inch water gauge, some TDC, TDF casing constructions, double wall, which typically is purchased, but there are fabrication details in the standard. And then other details cover, any curb, any access doors fabrication, eliminators and drain pan fabrication. And then there are also pipe penetration details within that chapter as well. And then plus there's commentary on all of the above. All right, so moving on from plenums and casings, getting back into large HVAC duct construction and supports. I know for those that were with us on the first seminar, we did cover large duct construction. So I'm going to just briefly go over it again. Figure 2-14 is has table 2-49, which covers duct construction options, requirements for ductwork over 120. Any side, that's less than 120, you would use the standard duct construction tables. So the main thing to point out on when you're constructing duct over 120 is, so tie rods are required at each joint and each intermediate duct reinforcement. So that's a little different than, duct that's less than 120. Sometimes, depending on what construction table you're looking at, would tell you if you need a tie rod or not. But when you're building over 120, tie rods are a requirement at each of those scenarios. So looking at table 2-49, so first, our top row here is going to be our inches of water gauge, our pressure, and that's either positive or negative. Our reinforcement size. So looking at this one here, an IT, I is our reinforcement, and then T indicates that, tie rods are required, like I mentioned before. And then we have our reinforcement spacings and our maximum tie rod spacing. So that's reinforcement spacings, 2.5 feet to 2 feet. And then our max tie rod spacing. So that's going to be, if it's telling you 5 foot is your max tie rod spacing, so you would take the width of your duct and then divide it by 5 feet, and that'll tell you, how many tie rods are required for that duct size. And if you don't like doing math, I I have created what I call a tie rod schedule. So this is something that's not currently in the Duct standard, but we're going to look to maybe add this in the next edition. So it's basically taking that this table, whoops, sorry, this table here, and then building out, your tie rod and reinforcement requirement for different size ranges. So be on the look out for that one in the next couple years to make its way in the standard, hopefully. So jumping into a quick example, I'm not going to go through the full example. What I really want to show with large ductwork that I didn't get to last time was duct supports. So I'll kind of fly through this one a little bit. But example one, if we have a 140 by 70 2-inch water gauge, we would come to table 2-49, get our 2-inch water gauge. Our panel gauge is going to be 18. Sorry, I got phones ringing, things dinging. Apologize. Panel gauge is going to be 18. Our reinforcement size is going to be an IT. Our reinforcement spacing, again, 2.5 foot. And then our tie rods. So that means if we're building a 5-foot joint, we would have our joint would qualify as a joint reinforcement. And then our intermediate reinforcement would be 2.5 foot, half of that 5 foot. And then our max tie rod spacing is going to be 5 feet. And that's how divided amongst the width. So if we came to the tie rod requirements for 2-inch water gauge, duct over 120, and we came to our size range, so we're 140. This schedule here is telling us we need 2 JTRs at the joints, and then, wow, my computer's touchy. Sorry about that. Keeps jumping ahead. Then we need 2 mid-panel tie rods plus the I-class angle. So for this one, the duct's going to be 18 gauge. Our joints, we're going to build it at a TDC, TDF. Our joint length is 56 inches. For the 140-inch side, the joints are going to be supported by 2 1-inch diameter EMT conduits spaced at 46 5/8 across the width. And they will be on each side of the joint. What I kind of took out of this example that was in the first go around was, how to size the EMT conduit, and that would be sized per table 2-38 for negative pressure, which we're not getting into today, but that's how we came up with the 1-inch diameter. And then our I-class intermediate reinforcement for the 140-inch side is going to be a 2.5 by 2.5 by 1/8 inch angle. That was sized using table 2-29. And then this intermediate angle will also be tied using 2 1-inch diameter EMT conduits, because remember, when building over 120, the joint and the intermediate reinforcement needs to be backed up with tie rods. And then looking at the 70-inch side, since this is under 120, we would have gone to these, what I'm calling standard duct construction tables. And the solution would have been 2 reinforcements on either side of the joint. And those would have been 2 by 2 by 1/8 inch angle. And again, those would be installed on both sides of the joint and on each side of the joint within 3 inches. The reason we wouldn't use tie rod in that situation is because, the tie rod would be 140 inches long, which would either make it, I don't even think you can do that. I'd have to look at the chart, but it'd probably be too big. So we'd have to go to an external reinforcement for the 70-inch side. And then this reinforcement would not need to be tied, and no intermediate reinforcements would actually be required. So kind of looking at this example, this detail, this kind of shows you graphically everything that's required. So at our 70-inch side, we would have the 2 angles on either side. So that's reinforcing our 70-inch side joint. And then our 140-inch side, we have our two 1-inch EMT conduits. And then at our mid panel, we have our angle with our two 1-inch EMT conduits. So what I really wanted to kind of get to with large duct work is the large duct supports. I just kind of wanted to highlight the construction really quick. So what we're looking at here, so this is figure 5-7 on page 5.15 out of the duct construction standards. So basically when you have table 5-3, to size your trapeze, really it only goes up to 144 inches in length. So when you are kind of beyond that with large duct, you either have to go to the rectangular industrial to size your hangers, which I'll also show, later on. But what you can do is within the standard, we have this figure, figure 5-7. And what it's saying is, hey, we can kind of redefine, how to size that trapeze based on a few things. So we have an L1 here and we have an L2 here. So that means we're going to add a third hanger, and that's either going to be at the midpoint through the ductwork, or another option is the L2 to actually tie into one of the tie rods, within that ductwork. So I'm going to go through a couple examples here on how to size, not only the trapeze, but also your hanger for large ductwork and staying within, the HVAC duct construction standard. So what we have here, we have option 1. So our duct's going to be 168 by 48. We're adding 3 hangers versus the 2. The duct would be 18 gauge. It would weigh 114 pounds per linear foot, and we're going to have a support or hanger spacing at 8 feet. So that means that the duct's going to weigh 912 pounds per 8-foot section. So what we can do is we can take this L1, which is going to be half of our 168, and then plus our dimension, from the hanger to the duct, which for this example is 3 inches. So this new L1 dimension is going to be 87 inches. So this L1 is going to now define our our half perimeter, to size our hangers from table 5-1. And then we're going to jump to that one. But and then the L1 dimension now defines our trapeze length to size from table 5-3. So now that we have that information, so we can come to table 5-1. Our half perimeter was 135. So, checking out the P divided by 2s, we have to go to 168 here because 120 is not big enough. So we would use the 168 row, and this indicates that we need a pair of 1/2-inch rods. For this one, we're going to use 3 rods. And then, basically you just need to verify that each hanger sized for 50% of the load. So we used our L1 to define our P2. And now we're using that L1 dimension, which was 87, to now size the trapeze bar. So we would come to table 5-3, using our 87 inches, coming over to the trapeze length. We have to use 96 because that's the first one. That's not less than the 87. And then, our weight calculated L1 weight is 456 pounds. So we would come across here, just size our trapeze. So we would come to the 600 pound, and then our trapeze is going to be 2.5, oops, by 2.5 by 3/16, because that meets also, the length requirement and our load requirements. So our option one solution would be based on table 5-1. We would have 3 1/2 inch rod hangers. And then based off table 5-3, our trapeze is going to be 2.5 by 2.5 by 3/16. Looking at our second option here, so this was, instead of using the L1 dimension, we're now going to use our L2 dimension. So again, same duct size, 168 by 48, 3 hangers, and instead of going to the midpoint of this duct work, now we're going to tie into one of the tie rods. So again, using all the same, 18 gauge, our duct's 912 pounds per 8 feet. We would take the L2 plus our DD, which is 2 inches for this one. And that again, that's going to define our P half perimeter, P divided by 2, for table 5-1. So P divided by 2 is equal to 162 inches. So our 114 plus our 48. And then L2 also defines our length, to select our trapeze from table 5-3. And that length is going to be 114. So based off of our L2 plus the 2 inches. So coming to table 5-1, our P divided by 2 is 162. Again, we're going to use the 168 row. Same scenario, half inch rods. We're using 3 of them, so we're going to be good. Then we would jump to our table 5-3, based off of our new L2 dimension of 114. We would use the 120-inch length row, and then come over. Really, our first option is the 3x3 by 1/4 inch, which is well exceeds our load of 611 pounds. So we would select the 3x3 by 1/4 inch angle, because this meets, both the length and the load requirements. Hopefully that makes sense to everybody, how we were able to kind of resize, the trapeze, and while staying within the HVAC duct construction standards, even though our actual duct length or duct width, I apologize, and our trapeze width kind of exceeded, just the, table 5-3. So the option 2 solution was, 5-1. We have 3 1/2 inch rods. Note, this is going to be coupled to the tie rod. So both, your tie rod's also going to have to be sized to handle that load as well. And then table 5-3, the trapeze is again 3x3 by 1/4 inch. And this is a bottom reinforcement, minimum trapeze size. So we have options to add a third hanger rod, either at the midpoint or tie into a tie rod to kind of minimize that trapeze size and your rod size as well. So if we were to size this out of the rectangular duct construction standards, so this is table 9-2. I'm just trying to show an example of what that angle would be. So if we used the last example and we said, hey, we have, 912 pounds times 174, that would have been our full span. So our full span would have been 168 plus 3 and 3, which would have given us the 174 inches. So we multiply those together and we get 158,688. So coming over to this table 9-2 support capacity for horizontal angle, this telling us we would need 5 by 5 by ½ inch angle versus the 3 by 3 by ½ inch. So as you can see, it significantly reduced our angle size requirement for that trapeze. But this is also an acceptable, acceptable way to size that support as well. Also in the rectangular industrial, table 9-1 has the same chart, although this is for horizontal channel, and it's either in the figure A dimension, flat, or B dimension, standing up. So you can size your channel and angle as well. And then also out of the rectangular industrial table 9-4, this is your hanger rod capacity. So this is giving you your rod diameter and the capacity of that rod, which is based in kips. So again, you would keeps jumping. You would multiply by 1,000, so that would be a 610 pound load on that for a 3/8 diameter, where a ½ inch rod would be 1,130 pounds. So hopefully that made sense to everybody. I know kind of went through that pretty quickly. If any questions pop up on it, I'll look out for it in the chat. All right, if nothing's coming through on it, we're going to jump into type 1 kitchen grease ducts. So SMACNA has a couple resources when it comes to kitchen grease ducts, kitchen ventilation, and food service equipment fabrication and installation guidelines. So this first edition came out in 2001. Boom. The second edition, 2026, is done. So that's been completed, and that will be available hopefully in the next month or so. Getting everything ready for printing. So second edition, keep an eye out for that, is going to be available very soon. A second resource for kitchen grease duct is the kitchen grease duct construction and reinforcement standards. So this first edition came out in 2022. And this is based off of 16 gauge black iron or cold steel. So we're going to be looking at this one to update it to include 18 gauge stainless as well. So this may be a end of 2026, beginning of 2027 project coming up. So a couple of things out of the kitchen ventilation. We have just a typical section view with your exhaust hood, your fire-rated floor and ceiling assembly, your grease ducts, penetrating your second story, seal around the duct at this point because of the fire-rated floor and ceiling assembly. Over up in the upper right-hand corner, we kind of have a upblast fan assembly detail. Just kind of gives you the nitty-gritty components of an upblast fan for a type 1 grease duct, and also a wall termination with upblast fan detail as well. And then 10-foot clearance to combustibles. You have your grease duct and your hood. So kind of the topics that we're going to cover here on grease ducts. Well, one, we're going to kind of look at the purpose of the grease duct, some of the governing codes, a type 1 versus a type 2 hood, And then we'll get into the actual construction of grease duct using the SMACNA grease duct reinforcement standard. And then we'll size, some of that, duct reinforcements based off of the duct construction, or not duct construction, sorry, the construction tables that are in that grease duct construction reinforcement standard. So, what is the purpose of grease duct? Well, it's to safely remove grease and smoke from the cooking process using type 1 hoods. And to direct the moisture, cooking heat, smoke, and grease vapors safely out of the building. Some of the governing codes. So the International Mechanical Code, the IMC, International Fire Code, IFC, and then the National Fire Protection Association, NFPA 96. These are going to be your governing codes. They, to provide the minimum construction requirements, for listed and unlisted, any installation requirements, minimum slopes, minimum clearances to combustibles, all that good stuff is going to be incorporated in these codes and standards. So first off, our IMC, International Mechanical Code. So this is section 506. Ventilation ducts shall be designed for the type of cooking appliance and hood served, constructed out of steel with a minimum thickness of 0.0575 inch or 16 gauge, or stainless steel, minimum thickness of 0.450 inches, 18 gauge. And again, we're going to update the construction standard to include 18 gauge stainless. Also covered in IMC is the joints, seams, and penetrations made with continuous liquid tight weld or brazed on the external surface. The types of connections, butt weld, welded flange, or overlapping, the telescoping or bell type. Defines, minimum air velocity to be not less than 500 feet per minute for the systems. 18-inch clearance to combustibles, 3-inch clearance to non-combustibles. And these are minimums where no enclosures are required. Looking at the IFC, the International Fire Code. So this code actually defers commercial kitchen exhaust hood compliance back to the IMC. Type 1 hoods are required at or above all commercial kitchen cooking appliances used for commercial purposes that produce grease vapors. There are some exceptions, for factory built systems to UL 710 and 710B, with integral downdraft exhaust systems. There's additional information on the operations, maintenance, ventilation systems, grease extractors, cleaning, and frequency inspections. NFPA 96. So this is the standard for ventilation control and fire protection of commercial cooking operations. So chapter 5 covers hoods, and then the construction, the type, sizing, any hood assemblies. Grease removal devices are covered in chapter 6. Any filters, device protection like baffles, drip trays. Chapter 7 covers the exhaust systems, including grease exhaust ductwork. Some of the general requirements are covered, clearances to combustibles, non-combustibles, any openings, access for cleaning, maintenance, the required materials, carbon steel, stainless steel, installation, welded duct connections, flange, telescoping, and bell type. One thing I do want to point out, so if you notice the IMC duct connections had butt weld, but NFPA does not have a butt welded joint type in NFPA. So it would only be a flange, telescoping, or bell type. And out of NFPA, here's a couple of figures for the different types. You have your telescoping type duct connection, the bell type duct connection gives you kind of minimum overlaps and ID, OD things. Also out of NFPA, we have what the flange with the edge weld, and this is going to be a maximum of a 1/2 inch flange. And then there's also a flange with a lap joint weld. So what that means, it's just basically the 1/2 inch plus a little extended flange, for welding purposes. So they're calling that the flange with lap joint weld. And here's all the chapters out of NFPA 96. Not going to get into all that, but there's quite a bit of information available at NFPA. So commercial kitchen hoods, type 1 versus type 2 hoods. Well, type 1 hoods are designed for commercial kitchen grease exhaust, minimum 18 gauge steel or 20 gauge stainless steel construction, all continuously welded. Type 2 hoods are designed to remove heat and steam and other non-grease applications. So whenever there's grease involved, you need to go to a type 1 hood. No grease, heat, steam. That's where a type 2 hood can be used. And then this minimum construction is going to be 22 gauge steel or 24 gauge stainless steel. So type 1 hoods must be used under these conditions and when smoke and or grease is being produced. So at all extra heavy duty, or medium duty appliances as defined by the model codes. When the particulate, including smoke and grease concentration produced by a single or multiple operation exceeds 5 milligrams per meters cubed, and that's averaged over an 8-hour period based on EPA test method 202. And then this is generally all cooking processes would generate this 5 milligrams per cubic meter. So, and then when any solid fuel cooking takes place, a type 1 hood must be used. Type 2 hoods are allowable according to some model codes, but only when there's no potential for smoke and or grease produced during the cooking process. So type 2 hoods are allowed under the following conditions here. Any light duty appliance as defined by the model building codes. When the heat from the cooking or warewashing operation results in an ambient temperature greater than 84 degrees Fahrenheit in the associated workspace. So this is to exhaust, any of that ambient heat out. When the moisture from cooking or warewashing operation results in an ambient relative humidity level greater than 70% in the associated workspace. And when the rate input of gas appliance or combination of gas appliances relative to the room volume is greater than 20 BTU per cubic feet in compliance with the National Fuel Gas Code. And then when indoor air pollutants produced by the cooking or warewasher operation exceed the threshold limits imposed by ASHRAE 62.1, ventilation and acceptable indoor air quality standard. So type 1 hoods can be used for all type 2 applications. but under no circumstance can a Type 2 hood be used for any Type 1 applications. So you can substitute a Type 1 hood for all Type 2, but it's not vice versa. You cannot use a Type 1 you cannot use a Type 2 where a Type 1 application is required. Here I'm throwing up a couple details from the SMACNA kitchen ventilation. This is out of chapter 2, figure 2-1, canopy hood, and then figure 2-2 canopy hood components. Some components you might come across, baffle, filter, your grease collection, outside of your hood. So that's going to be your welded, continuous welded. And then here we're showing a minimum height above the floor of 6 foot 6 inches. What we've put in the new release standard is we've kept the 6 foot 6 inches, but we added a note, as required by local code or something like that. Also in chapter 2, we have table 2-1. So this is just kind of showing various configurations for the welded perimeter requirements of Type 1 hoods with makeup air discharge. So essentially what these details are telling you, dependent on how that makeup air discharge is tying into the hood, would tell you if a fire actuated damper, or multi-blade fire actuated damper is required. So anytime that makeup is actually penetrating the, continuous liquid tight welded construction, that's when you're going to have your either fire damper or multi-blade fire damper. So as you can see, detail F, this makeup air is not penetrating the welded, continuously welded construction, so no fire dampers required, but the actual grill is penetrating that, so a multi-blade fire actuated damper is required. And this is also found in NFPA 96 Annex A. Same details are in there as well. Here we have out of Chapter 5 of the SMACNA kitchen ventilation. So this is just the minimum airflows for the different types of hoods: extra heavy duty, medium duty, and light duty. Also, we've added some, temperature ranges. So 700 degrees Fahrenheit for, hold on one second. There we go. For our extra duty, 600 for heavy duty, 400 for medium duty, and then 400 for light duty appliances. So type 1 grease ducts, some things to consider. These are out of the SMACNA kitchen ventilation, chapter 3. Your clearance to combustibles, access for inspection and maintenance, obviously dimensional stability, leakage control, vibration and noise, any possible exposure to damage, weather, temperature extremes, and so forth. The support and reinforcement of that Type 1 kitchen grease duct system. Any seismic restraint requirements, those would definitely be defined within the project specifications. Any thermal conductivity. Type 1 grease ducts, it connects to a Type 1 hood. It's going to direct the contaminated exhaust out of the building. This is not going to be interconnected with any other exhaust system. Again, must be welded liquid tight. size to convey the right amount of exhaust air. You want to make sure that the minimum feet per minute's going to be per the codes. I think it was 500 feet per minute, if I'm not mistaken. And then again, our construction options, 16 gauge steel or 18 gauge stainless steel, NFPA, and the International Mechanical Code. Our minimum installation slope, quarter-inch per linear foot, or about a 2% grade on horizontal runs, less than or equal to 75 feet. And then any run that's over 75 feet is going to be a 1-inch per linear foot, which is an 8.3% grade on horizontal runs. Obviously, they need to be installed. The duct system needs to be installed without forming dips or traps. Any low points, exceedingly long runs where you have to kind of sawtooth, you're going to have reservoirs at those low points. Absolutely no dampers shall be installed in Type 1 grease duct unless specifically listed and labeled for such use. You're going to want to lead, the exhaust as directly as practical to the exterior of the building, taking, I guess, the shortest route possible. A couple of comments on access panels. It's going to be the same material and thickness as the duct, located either on the sides or the top of the ductwork. For horizontal runs, they're required at each change in direction, 23-inch and under every 12 feet. That's the duct dimensions. And then any duct over 23 inches, one single door can be installed as long as it's large enough, for personnel to enter. Access doors are required 3 feet on either side of a fan or 3 feet within a wall-mounted fan, or within 3 feet of a wall-mounted fan. Sorry about that. And then on vertical ducts, they're going to be required at every floor unless one is large enough to enter at the top of the riser. Then you only need one. And then any hoods with integral dampers, you would need an access door within 18 inches of that damper. That's for maintenance, cleaning, and so on. Here we have figure 6-1, access panel assembly. This is out of the kitchen ventilation SMACNA document. One thing to point out that the access door must be labeled with access panel, do not obstruct. And then also new to that document that's going to be in the 2026 edition, we've added figure 3-2, type 1 grease duct reservoir. So this provides, a detail of that reservoir, and then also kind of some of the requirements, based on code. Construct is required for the grease duct they serve, be located on the bottom of horizontal grease duct or the bottommost section of the grease duct riser, must extend across the full width of the grease duct, minimum 12 inches wide, have a minimum depth of 1 inch, and bottom that slopes to the drain. And then you must provide a clean out, directly at the access to the reservoir, either on the side or the top of the duct to permit cleaning. So this is a new detail that we have. All right. So now we're going to get into actually constructing some grease duct, or I should say adding, reinforcements. What requirements are there for reinforcements? We get a lot of questions, on what the reinforcement requirements are for grease duct systems. So that prompted, SMACNA to generate this first edition out of 2022. And again, this one is solely for 16 gauge. The next edition, we're going to go in and add 18 gauge stainless steel. So the purpose of this construction reinforcement standard was to, generate tables to make the selection process less tedious. Again, it was based off of 16 gauge carbon steel. Duct dimensions are going to be, up to 96 inches. The pressure capacities for positive and negative, can be used on the makeup air side as well. But pressure capacities are 2.5, 3, 4, 6, 8, and 10-inch water gauge. Some very limited information for 11-inch water gauge, like literally up to 12 inches unreinforced. So that's it. And then it's going to be based on reinforcement spacings of either unreinforced, 2, 2.5, 3, 4, 5, or 6 foot reinforcement spacings. So table 1, which we're going to look at here in a second, this is the maximum static pressure capacity in inches water gauge for carbon steel grease ducts operating at temperatures up to 500 degrees. So there's an allowance in this table of 5.2 pounds per square foot for wrap and other loading, which again is equivalent to 1-inch water gauge. Each side can be independently reinforced. Reinforcements do not need to coincide. And then, hot rolled cold steel, cold rolled, galvanized, and aluminized steels are covered. So here we're looking at table 1. This is our reinforcement. So what this is, if you've ever looked at the rectangular industrial, it's the construction tables are a little bit different than the duct construction standards. So what these numbers are telling us here in the table are, this is the inches water gauge capacity of that duct dimension at these reinforcement spacings. So for instance, if you have ductwork, built at a 16 gauge carbon steel, 12 by 12, unreinforced, that can meet a capacity of 11 inches water gauge versus 13 to 18 inches unreinforced would only be 4-inch water gauge. Once you start adding reinforcement, 2 foot, 2.5, 3 foot, these are the pressures that those panels will handle with that reinforcement spacing option. So it's a little different than the duct construction standard tables. So if we looked at an example here, a pretty easy one. Again, all these examples are going to be 16 gauge carbon steel. So this first one, we're saying, hey, we're going to build a 12 by 12 kitchen grease duct, 10-inch water gauge. We would come to table 1, check out our duct dimension here. And then again, our unreinforced capacity is going to be 11-inch water gauge. So our solution is we can use up to 11-inch water gauge, 16 gauge cold steel, 12 by 12, no reinforcements required. So that's pretty simple solution. Now, if we look at something a little bit bigger, here we're going to have 48 by 12, negative 4-inch water gauge. So again, we're back on table 1. This is just part of it, but we're going to look at the 48-inch size. And then we're going to come to right here, and this is saying at 4-foot reinforcement spacings, we're good up to 4-inch water gauge. So on the 12-inch side, obviously we know from the previous example, that's good up to 11-inch water gauge. We're not going to have to worry about anything. But the 48-inch side is going to need a reinforcement. and that reinforcement spacing is going to be 4 feet. So now that we know, hey, we need something every 4 feet for that 4-foot side, table 2 through table 7, these are your reinforcement code requirements at the maximum pressures, capacity for the reinforcement spacing that we selected. These tables have really, really long names. I apologize for that. But if we went to table 4, so this is the 4-inch static pressure table, looking at the 12-inch side of that 48 by 12, what this is telling us is we're okay. We don't need any additional reinforcements. They can be unreinforced. So 12-inch side does not need reinforcement. Again, the 48-inch side does need reinforcement. And we picked 4-foot spacing, and that gave us our 4-inch water gauge capacity. So if we jump back to table 4, we look at our 48-inch duct dimension. As you can see, the first thing we come to is the 4-foot reinforcement spacing, and that's telling us we need an R for reinforcement. If we looked at 3-foot spacing down to 2-foot, we could get away with an R3 reinforcement. And anybody familiar with the industrial duct construction knows, the stiffeners are R1, R2, R3, R4 versus an A, B, C, D in the HVAC duct construction standards. So 48-inch, we need an R4 at 4-foot spacing. So we would use a type R4 at 4-foot spacing or a type R3 at 3-foot and below. So now we know, what we need. We need an R4, but we need to figure out, what is that? What is an R4? What is an R3? What are those requirements? So now we would use table 8. This is stiffener data for structural steel, cold steel. This is our reinforcement options. Kind of zooming in a little bit closer to our R3 and our R4. So R3 was at 3-foot reinforcement spacing, and the R4 requirement was at the 4-foot spacing. So this is going to be our angle options. We can select from any one of these R4 to, qualify for the reinforcement at that particular spacing of 4 feet. So we could use a 2 by 2 by 3/16 or a 2 by 2 by quarter. So kind of wrapping up the whole solution here, 48 by 12, negative 4-inch water gauge, 12-inch side doesn't need any reinforcements. 48-inch side, we're going to add reinforcements at 4-foot maximum spacings. And then that can be either the R4 at 4-foot or again, an R3 at 3-foot or below. So also in this duct construction grease duct reinforcement standards, we have details for attaching the reinforcing stiffeners. Figure 1 is an unfixed reinforcement stiffener heel down. Couple things to point out. You want to use a 2-inch weld at 8-inch alternating heel toe spacings. And then the welds must occur on either side, of that angle of each side of the stiffener. Figure 2 is just a fixed reinforcement stiffener back to back, heel down. You want to weld the 2 parallel edges here of those. And then again, we have the same attachment or fastening requirements of 2-inch long welds, 8-inch on center. Whoops, wrong button. Figure 3 is for fixed reinforcement stiffeners, framed heel down. Again, same 2/8 requirement, alternating heel toe. And then figure 4 is the fixed reinforcement stiffeners back to back heel down option. And then we cover flange joints within the duct construction reinforcement standard for grease duct. Figure 5A is the even flange joint. And again, that's a maximum height of 1/2 inch. And also permitted what we're calling the uneven flange joint, which I showed you earlier out of the NFPA 96. So this is a uneven flange. And then your the height of the uneven part is going to be 1/2 inch or H plus 1/2 inch. Type 1 grease duct supports. So grease duct supports, non-combustible duct bracing and supports shall be securely attached to the structure and designed to carry gravity and seismic loads when required within the stress limitations of the building code. No fasteners can penetrate the grease duct. And also, anytime you have a duct cross section that's 24-inch or greater in any direction, you're going to have to add, design for the duct weight and 800 pounds at any point of that grease duct system. So that means, you're going to have to heavy up your duct supports is what that means. And then type 1 hood supports. So this is going to be secured in place by non-combustible bracing and supports that are adequate for the hood load, unsupported grease duct, and any effluent loading and the weight of personnel. And then type 2 hoods supports secure in place with bracing and supports that are adequate for the hood load, unsupported ductwork, effluent loading, and the weight of personnel as well. And with that, I've finished up a couple minutes early. So if there are any, we can open up to any questions either about this seminar, previous seminars, or anything unrelated. We're here.
You can go ahead and unmute if you want to ask Jeff some questions while we have him still.
Anyone?
Thank you,
Come
Jeff. I
on.
don't have any questions. Sorry.
Oh, that's all right. But if you think of something, obviously, please take down my email, my contact information. More than happy to assist where we can assist. And we just cover a whole range of questions. Even if it's not SMACNA document related, we try to help members out as much as possible in any way we can.
Thank you so much, Jeff.